This paper is about using latent factor models to discover structure in high-dimensional datasets. fMRI data, for example, might have over 100,000 variables, but might have only a handful of samples for each individual. Existing latent factor methods either fail to recover structure in this type of undersampled data, or they're computationally intractable on such high-dimensional datasets. We propose a modular regularization scheme that allows us to find plausible structure in high-dimensional datasets in a computationally efficient way. The idea behind our approach is to start with an unconstrained latent factor model like the one on the left. What we'd like to do is encourage that model to be as modular as possible, like the one shown on the right. In the modular latent factor model, each variable has only a single latent factor as a parent. If we were to search over all the modular latent factor models, there would be exponentially many of these discrete structures, making this totally untractable. Instead, we do an optimization over the unconstrained latent factor models, but we add a modularity regularizer, which encourages the models to be as modular as possible, like the one on the right. The idea for this regularization term comes from the observation that the modular latent factor models have an equivalent characterization in terms of some information theoretic criterion. So we use these to construct our modular regularizer. When we apply this to high-dimensional data, we see that we recover structure better, especially as the number of variables increases. The y-axis shows how well we've recovered clusters versus p, the number of variables on the x-axis. Our paper actually shows sample complexity bounds that this recovery problem is impossible if the dimensionality is too low, but as the dimensionality increases, it should be possible. Our latent factor method is the only one that is able to leverage the structure in the high-dimensional data. Another way to use latent factor models is for covariance estimation. If the number of samples is less than the number of variables, we know that the empirical covariance is a very bad estimate. So what was usually done is to use additional priors like sparsity. We show in our paper that on real-world datasets, our approach outperforms GLASO and sparse PCA for covariance estimation on 50 out of 51 undersampled datasets from OpenML. We also show some results on stock market data. We're able to better estimate the covariance matrix using a small number of samples, and the latent factors that appear align well with known structure in the stock market. Please have a look at our paper for all the details. We derive the information theoretic objective that encourages modular latent factor structure, and we show applications in a number of domains, including neuroscience, finance, and gene expression. And finally, we also include theoretical bounds and sample complexity.